Our first case study involves the acquisition of sound categories. We'll restrict ourselves to English vowels, and we will constrain the representation of vowels to a two-dimensional continuous space of the first and second formants. Recall that the formants of vowels are the regions of the frequencies of peak energy as the vowels are produced. You can see examples of this in the upper right-hand part of the screen. In the lower left-hand part of the screen is a collection of vowel productions that was elicited and recorded in a classic study nearly 70 years ago. These are cases where the scientists simply had native speaker participants just say particular words, and the vowels and the words are recorded. So we get labels for them because we know, we as native speakers of English and as researchers, know what words the participants were asked to produce. But if we turn this around from a learning perspective, when a very young child is listening to the language in its environment, it doesn't know the words yet. And as you can see, the sound categories are very badly overlapping in this continuous format space. So there's actually a significant learning problem for a learner who doesn't have the labels like children don't, which is, well, how can they learn the vowel forms? That is, how many categories there are and where each category is located, when they don't know that different labels, which of the different labels are attached to which examples. Now, this we will distill down to the more general problem of category learning in continuous space, which arises in many problems in machine learning, artificial intelligence, and cognitive science. So this is a much simpler example that you see before you. There is a very good separation between two densely populated regions of the space. And you might think that this will make the learning problem quite trivial. But actually, already with this very simple example, there are some non-trivial challenges, because what we need to do is we need to have an algorithm that will, in very general circumstances, come up with a robust and reproducible for different learners to learn different things with slightly different input, a robust and reproducible computational mechanism for collecting a large number of observations like this and distilling them down into a set of categories that have structure, that have shape and orientation and so forth. So, for example, one of the simplest things you might do is draw a minimal bounding box right around each category and call that the category. And so that would, we'd have to punt on how large a division between points is allowable to create a distinction between categories. But that might, if we punt on that problem, we might seem to have a pretty good solution here. But actually, this idea, this is what is sometimes called a highly non-parametric method, because the bounding box is as the number of examples grows, the shape of the bounding box could become more and more complex and odd. And so there was actually a pretty non-parametric method that was explored in a paper, for example, about 13 years ago on what was called topographic online mixture estimation and for vowel categories. So in this version, this is a histogram of point values in a particular unidimensional space, and the idea was simply you incrementally look around for regions of low density, and you design category boundaries that are low density, and in points of areas of high density don't introduce category boundaries. So this would have the property of distilling this down into three continuous categories with some boundaries in between them, which seems sort of intuitive. So that seems like it's all right, but there's clearly some limitations. So if we tried to apply something like this to the vowel situation, it seems very plausible that we might wind up with just one giant complex shaped category. We need to have some method of avoiding doing that. And one possibility, which is a pretty compelling idea, is that we want to have a strong inductive bias for the shape that a category will have. That a category in a space, at least for a vowel space, doesn't necessarily have some odd, wiggly, jagged character. Instead, it should actually be a pretty regular and simple form. So one candidate for a simple form is a Gaussian distribution. And so one classic approach to this problem of learning categories in a continuous space with unsupervised methods is the mixture of Gaussians approach. That is that the assumption of the data arising from a mixture of individually Gaussian categories. So we say, no, this kind of arbitrary weird jaggedy shape is not allowed. Instead, we have to have these well-behaved categories. Here, what I'm showing you is what's called the characteristic ellipse of two different Gaussians with two different means and orientations, but pretty similar sizes. The characteristic ellipse is an ellipse of equal probability density for a Gaussian mixture model, and so long as you agree on what that probability density is, then you can use it to intuitively visualize different Gaussian categories. So here's a directed acyclic graphical model, a visualization of a mixture of Gaussians model. And it has a little bit of new formalism above and beyond what we've seen for directed acyclic graphical models to date. And I'll explain that here. So this is a generative story of how data comes about in the world. And the starting point is that by assumption, there are in the world a set of Gaussian categories. Let's say that number is M. And each category has its own mean and covariance matrix. The mean is mu, the covariance matrix is sigma. And the mean will determine the position of the ellipse. The covariance matrix, sigma, will determine the size and orientation of the ellipse. Each category has a prior probability. So in addition to these categories, there's a multinomial distribution over M categories. What that means is that if you draw a token at random from a collection of utterances or a collection of data, then the probability that that will be of any particular category is determined by that category's multinomial probability. N is the number of data points. So these square plates here that you see here are, these are called plates. And this is what's called plate notation for directed graphical models. And the idea is that whatever is inside the plate is replicated the number of times of the index number in the corner of the plate. So there are M categories with sigma and mu. So there will be a sigma 1 through sigma m, a mu 1 through mu m for the M categories. And there are N data points. Now, each data point has a category, which is something that is unobserved, of course, because we as the learner don't see the category indices. But it also generates a data point, and the role of the category index I is to pick out the relevant mean and covariance matrix, mu sub I, sigma sub I. You condition on those, and then the data point comes from a multivariate Gaussian from that distribution. And so now we're in the position typically of inferring phi, the sigmas and the mu's from the data Y. And the standard inference techniques that we might think about for this are, of course, our handy maximum likelihood, where we estimate the sigmas, the mu's, and the phi as the settings that will put the maximum probability on the data. The second that we might consider is Bayesian inference, where we put a prior on sigma, mu, and phi, and then we infer a posterior on those things given the data Y by reconciling it with the likelihood Y given the parameter values. However, for unsupervised learning problems, there's often a big challenge for maximum likelihood, and it's a very severe challenge in the case of continuous data. And the major problem, I think, can be easily visualized by looking at things in one dimension. So imagine we're in a one-dimensional scenario. Here's our data, and we want to fit a mixture of two Gaussian categories to this data. Okay, and it's not immediately obvious what you would do here. So, for example, one intuition might be that you would maybe put a couple of data points here and maybe a bunch of data points here. You might alternatively try putting a distribution here and maybe an overlapping distribution here. Those both seem like intuitive solutions. However, neither of those is actually anywhere near the best solution. So let's just focus on any one arbitrary data point. I'll happen to choose that one. And let's imagine putting this particular Gaussian over that point. Okay, so that's okay, but I could do better by making the covariance matrix, the standard deviation of that Gaussian narrower, because I'd be putting a higher likelihood. So the green peakier Gaussian will have a higher likelihood than the blue less peaky Gaussian. But I can keep on going, higher and higher. And the problem here is that as I make the Gaussian's variance smaller and smaller, the likelihood gets higher and higher of that individual data point. And so actually the very best thing I can do is to just choose one data point and put a zero variance Gaussian right on that data point, which will give it infinite likelihood. And then just use a very diffuse flat Gaussian to clean up the rest of the data points. This indeed will be a maximum likelihood solution. And in fact, no solution that assigns more than one observation to all of the categories is going to give you a maximum likelihood solution, because you lose out on this opportunity for infinite likelihood. So this is not a viable way of learning mixture of Gaussian models, maximum likelihood. It's used sometimes in practice, but insofar as it gives you decent solutions, it's because it didn't find the actual maximum likelihood solution. So then arbitrarily narrow Gaussian category can assign arbitrarily high likelihood. This is a big problem. In a two-dimensional setting, this would mean that instead of this natural solution, what would be preferred is, for example, a solution that has this very diffuse Gaussian over most of the region, and then this second Gaussian in green in the upper left, which just targets one category and is an infinitely small variance distribution. And that, once again, would give infinite likelihood to the data. So that's a big problem. Instead, what's preferable is Bayesian inference over a mixture of Gaussians. So we start off with mostly the same stuff. We have the multinomials over categories and the Gaussian parameters for each of the categories, the index I, the number of data points, and the data points are observed, the Y. But we have these additional two components. The first one is a prior distribution over category probabilities. And so this, just think sigma sub phi just means some kind of prior over likely phi's. And this is often in practice what's used is the Dirichlet distribution, which is a generalization of the beta distribution. We'll review the beta distribution a little later today. The Dirichlet is a multinomial version of it. And so it's a prior over multinomial probabilities. The second part is this prior over Gaussian category sizes and shapes. For simplicity, we'll just denote this as alpha. And to summarize, the role that alpha will play is going to be of the form of don't expect to have tiny categories. The point here is that we have to penalize via the prior. So since the likelihood of the prior in a Bayesian inference are reconciled against each other, the opportunity for infinite likelihood that you would get by having an arbitrarily small Gaussian over one data point has to be counterbalanced by an arbitrarily low prior probability for an infinitely small Gaussian. And so we will use models that will do that. However, in order to deal with this, we'll have to use conjugate priors. And I will take a break now and I will explain conjugate priors to you in a moment.